good morning. First, let me thank the organizers for inviting me. When they invited me, they asked me to give a tutorial talk on loopholes in Bell experiments. So, okay, I prepared something along those lines, but I thought it wouldn't make much sense to, really talk about loopholes in Bell experiments while not explaining Bell experiments in themselves in such a tutorial talk. So, essentially, I will start with that. It will be a quite, in fact, long discussion on this topic. So, for those of you who know already all about it, I apologize. And so after that, I will then discuss more in detail loopholes in Bell experiments and their relevance in certain applications. So maybe one thing I can say is that this year is rather special for this kind of topics because it's the 50th anniversary of Bell's theorem. So it's already quite an old discovery. But it's interesting to know that even, although it's already half a century old, it's still a very timely topic, and there are still many contributions in this area. And I think this you can understand from 2 points of view. So first, experimentally, people are now getting close to a final test of Bell's inequality, a loophole-free test. And well, I think there are good expectations to see such a test be achieved within 1 or 2 years. On the other side, from the more theoretical side, there have been a big new class of applications which have been developed in quantum information, which are based actually on Bell's theorem. So these are called device-independent protocols. And this has also motivated, again, the extensive study of these concepts. All right, so let me give you the outline of what I will do in this tutorial. So as it's still quite early, I will start with a rather long warm-up on Bell's theorem. I will tell you about the CHSH game. Then I will discuss the concepts of locality à la Bell. Then I will talk a bit about quantum non-locality, Bell's theorem. After that, I will review some of the key experiments in this area, discuss then some of the loopholes, and then their relevance for applications. All right, so the beginning of the story is like this. We are going to be talking about correlations. So you have the following setup. You have two physicists, Alice and Bob, which are in separated locations. And now each of these observers is given a device. So there is some provider that gives each physicist a device. And you see, these devices, well, they look identical. Essentially, there is a controller here on this device, which allows the observer to choose which measurement to perform on the device, which questions he want to ask to the device. And then after that, he can read the result or the answer to this question here on a meter. And it's exactly the same here on Bob's side. But you notice that apart from that, one has no idea how the devices work. They are just black boxes or blue boxes here, if you want. So now, Alice and Bob start the experiment. They play with the devices, so they choose different measurements, note the result, and so on. And after a while, well, they meet together and compare their data. And what they see is that there are some correlations in this data. So for instance, when they chose the same measurement, they obtain the same result. So this is a form of correlation. So of course, the thing you want to know then is how does it work? What is the mechanism implemented in those boxes that explains those correlations? So the first idea that they have is that this is due to some form of signal. So this means that once Alice has chosen which measurement to perform here, then there is some signal that is emitted to the other device, and then that informs it of Alice's choice, in which case one would indeed expect to see correlations. So then you may ask, well, can this hypothesis be tested? Well, of course it can. What you would do is then you would place those two devices sufficiently far apart and make measurements in a very synchronous manner in order to reach a space-like separation between the two the two places. And if you still observe correlations, well then, at least if you believe in relativity, well then you will have to admit that no signal can explain the correlations that you observed. But then you may think, okay, there might be actually another explanation to, so if those correlations do not originate from a signal, how could they have been created? And there is indeed a simple alternative explanation, which is that there might be a common strategy explaining this correlated behavior. And this is indeed quite natural because the devices have been made by the same provider. So he could have implemented a program inside, which, when each observer then chooses some question, would then deliver some answer, and this will be indeed done in a correlated manner. So here we talk about pre-established correlations. And now the question is, can we test again this hypothesis somehow? And this was the question that John Bell asked, and that he solved then by presenting his famous inequality. And this brings me now to the warm-up of this talk. So here is the test, or the game, if you want, which is now known as Bell's inequality. And this game will allow us to test the hypothesis of a pre-established strategy. So is the correlated behavior that we observe due to a common cause? So here is our experiment. We have again Alice and Bob. And now I have shown you here the rules of the game. So it's a quite simple game. It's a game in which there are only two questions, or two measurements if you want, two settings for this controller here. And for Alice, we are going to denote these questions x0 and x1. And it's the same thing for Bob, two questions, y0 and y1. And then the answer to each question is just binary. So we have two answers here, and this is going to be +1 or -1. And now we are going to ask, so these are the rules of the game, if you want, that there are certain relations which are satisfied between the answers to each questions, depending on which pair of questions has been asked. So this is what we are going to demand now. So let me explain you what this graph here means. So first, you see here we have the two questions of Alice, x0 and x1. And here we have y0 and y1. And now we are going to demand, for instance, for the first pair of questions here, for x0 and y0, we are going to demand that the answers are the same, or that they are correlated, if you prefer. So note that it doesn't matter what this output is locally here. It could be +1 or -1, that we don't care. But what we care about is that that outcome is the same as this one. So it could be +1, +1, or -1, -1. That would win the game. And now, you see that for other pairs of questions, we ask similar relations. So for x0 and y1, we are also going to demand that the outputs, that the answers are correlated. For x1 and y0, same thing here, correlations. But then the tricky part is the last one. So for questions x1 and y1, we are going to demand that the answers are opposite, so that they are anti-correlated. So again, it doesn't matter if it's +1 or -1 locally, but we want different answers, so +1, -1, or -1, +1. All right, so to really understand why this game is a bit tricky, the best thing is to try to play it, actually. So imagine now you are the provider, you are the person who prepared those devices, and you know that Alice and Bob are going to play this game, and your goal is to create the devices, to program the devices in a way to achieve the best possible score. So you want to satisfy the largest number of relations in this game here. So the first thing we need to do is to come up with some answer for this question here, for x0. So here, because we are starting, it doesn't really matter. But we are going to just say that we will program the device to give output +1 here. Now, the next thing we need to find out is what is the output we need to program for measurement y0. So of course, if we want to satisfy that relation, obviously we need to output +1 as well. And now, if we ask ourselves what do we want to output here for x1, well, to satisfy this relation, we need +1 again. And then finally, what do we need for y1? Well, to satisfy this relation, we need +1 again. And now you see why the game is tricky, because indeed the last relation here, I mean, we have no more choices. All places have been filled with answers. And here we have a problem, because we wanted opposite answers, but these two answers are actually the same. And you can turn this game in every possible way around, starting from every possible question. But I won't do that, but you can convince yourself that essentially you can never satisfy all four relations at the same time here. So this game is a frustrated chain, if you want. There is no way to assign outcomes in a deterministic manner that will perfectly fit. All right, so essentially, I hope I have convinced you that the best possible score you can achieve at such a game, by considering such a classical strategy, is 3/4. So you can never do better than 3/4. There will always be one of these relations that will not be satisfied. Good. So this is the CHSH game, or the CHSH inequality, if you want. The inequality could be understood as this one, if you want, but we will make it more precise. Now, you may have encountered this object in other contexts, and probably in some different form. So here is a more formal way of writing it down. We are going to use the notion of a correlation function. So for every pair of measurement, here for measurement x0 and y1, we define the correlation, which is just the expectation value of the product of the answers. So it means it's the probability that the answers are the same minus the probability that the answers are different. Just a simple correlation function. And in this language, the CHSH inequality is defined like this. So we define some quantity here, which I call CHSH. And this is a sum of 4 correlation terms, with the particularity that there is a minus sign here. And now if you look at this expression, well, you see that it exactly corresponds at this game. So for instance, for pair of measurements x0 and y0, I wanted correlated answers. So I take the correlation here with a sign plus. So my goal will essentially be to maximize this quantity. Before I wanted to maximize the score, this is the same as maximizing this quantity. So if I have correlated answers here, I have +1 there. If I do here and here as well, I will have +1 and +1. And then if I manage to get opposite answers here, this term will take value -1. So the two minus signs will cancel, and I will get positive contribution. And now, we saw before that for classical strategies, there is a limit to how well you can do at this game, which was that you cannot satisfy more than 3 relations. And therefore, you see that this quantity here, so if you satisfy the first 3, for instance, but not the last one, so you will have 1 + 1 + 1 - 1, then you get 2. So this quantity is always upper bounded by 2 for any classical strategy. And this is the famous CHSH Bell inequality. So note that this inequality here is not due to Bell originally. Bell had a slightly different one. It was more complicated. But a few years later, so in fact 5 years later after Bell's famous work, Clauser, Horn, Shimony, and Holt came up with this version of Bell's inequality. All right. I should also say that because this is a tutorial, you should just interrupt at any time if there is a question or something that's not clear. I try to make it as clear as possible, but if there are still questions, do not hesitate. All right, so the next thing I want to do is to make this a bit more formal. So the idea is now to introduce a condition of locality. You saw that in the previous game. Why do we have a frustration? Well, it's essentially because the two observers are separate. They cannot communicate during the game. So to make this formal, we are going to introduce some notion of locality, which people now refer to Bell locality in order not to mix it with other notions of locality that are important in physics. So it's important that, I mean, in certain communities, people understand locality as the absence of a signal from one place to the other, what we would call no signaling. But so in this work, locality has a different meaning, which is going to be made precise here. Okay, so we start again from our simple experiment. So we have, we have our observers here with devices, which they can test. Now you see here, there is some source here that represents the fact that there might be a pre-established strategy in those boxes. So this may represent some particles that go inside the boxes here and there. And now, well, we let each observer make a certain number of experiments. So X denotes the choice of measurement settings, A denotes the outcome. Here, the same thing, Y, the choice of measurement for Bob, and B, its outcome. So as before, you imagine that the observers play with the devices and so on, and then after a while they acquire some data, and this data is a joint probability distribution. So it's a probability of any pair of outcomes A and B, given any possible measurements X and Y. All right, and now the question we ask is, well, can we explain this data by a local model, right? So somehow the idea is that there is sort of no, I mean, these places are in a space-like separation, and we would like to define a natural notion of locality. So here is what Bell proposed. Well, he proposed to say the following thing. In such an experiment, the pre-established strategy might be due to some common variables which we are not aware of. So John Bell called that local hidden variables. So these variables here, which I represent by lambda, you can think of them as the program that is inserted in this device here and that is going to provide an outcome B given measurement Y. And the idea is that because I'm not aware of these hidden variables, I need somehow to average over them. So essentially, the probability distribution I observe here, this is the average over some distribution here of hidden variables, p lambda, which is arbitrary, and then the probability distribution of outputs given inputs, given a specific value of the program, right? So this is the quantity I'm interested in. And now Bell's idea was to say, well, this thing here, so once I fix the value of the hidden variable, once for a specific program, the response function here, so the way in which the output is computed from the input and this hidden variable, cannot depend on what is on the other side, on Y and B, because of the separation. So you see the assumption behind Bell's locality is at this point. You say that this quantity here it factorizes, so it's equal to this product here. So the response function of Alice, so the probability of A given X and lambda does not depend on B and Y. And similarly on Bob's side, the output is produced using only the input and the hidden variable. Right, so that's the assumption of Bell locality. And you know, so of course, now at the end of the day, we're going to see that in quantum mechanics, there exists data, there exist these experiments, the data of which does not admit a decomposition of this form. But then, you know, you may think, okay, every now and then on the archive, you see papers claiming that quantum mechanics is local and that people have missed something and that Bell didn't see something. Well, essentially, this is always due to the same reason. I mean, in most cases, the cases is that what those people use as a definition of locality is not this one. So of course, if you talk about something else, then you know results might be different. But once you have this definition of locality, then it's a simple mathematical problem to show that quantum mechanics is not a local theory, but again using this definition. All right, so now the idea is the following. So we have our definition of locality, and the main point is that Bell showed that local correlations, so any set of data that admits a decomposition like this will necessarily satisfy a set of inequalities, a bit like the one we saw before, the CHSH one. And these set of inequalities are called Bell inequalities. So CHSH is the most used one, perhaps the most useful one also for most purposes. It's also the simplest one because it has just 2 measurements and so on. But really, you can imagine an experiment with 10 measurements for Alice, 15 for Bob, and outcomes which are ternary and whatever scenario you would like. And then there are all sorts of inequalities, which are generalization of the CHSH one, which form this big set of Bell inequalities. In general, we do not know actually if this set is finite. There might be an infinite number of Bell inequalities. Okay, and now the point is that if you obtain data that violates one of these Bell inequalities, well, then you have what we call Bell non-locality, because you cannot explain your data by decomposition like this, right? So local correlation must satisfy all inequalities in some very big set. Now, if just one of these is violated, then it's enough to conclude that your data is non-local. Right. So as I'm sure you all know, in quantum mechanics, well, we can actually create data that is non-local, so that does not admit a decomposition like the one we had before. So in order to do that, well, we need to come up with some quantum strategy, and this is going to include two elements, right? So the first element is that the source here is going to be replaced by a quantum one, so now we have access to entangled states, which is going to be one of the main ingredients. So we will need an entangled state here. In this example, I'm going to just use the 2-qubit singlet state here. And then we need another ingredient, actually, which are the local measurements. So once the particle comes inside this box here, well, the observer here, Alice, chooses measurement 1 or 2, right, as before. Now, in order to deliver some output here, you need to perform a measurement on this particle. And if we want to describe a quantum strategy, we'll need to say what they are. So these local measurements in this particular case here are going to be the following. So for x0, I'm going to choose the measurement sigma z. So I will represent measurements by Bloch vectors here. It will be simple for the analysis that will follow. Measurement x1 here is chosen to be sigma x. And then for Bob, I'm going to choose measurements which are somehow intermediate between x and z on the Bloch sphere. I forgot about normalization here, but well, you can see that these measurements are somehow in between. Now, you need to remember one simple thing, is that when you perform measurements given by vectors a and b on the singlet state here, well, the expectation value is just given by minus the scalar product of the 2 vectors, right? Now, once we have this here, well, then it becomes completely trivial now to calculate how good this quantum strategy will perform at the CHSH game that we had before. Note that here I have put, so here is an equator of the Bloch sphere, and I have put the 4 settings here that you can see the Bloch vectors. Good. So now what we want to do is to see how good we do at this CHSH game. Remember there were these 4 correlation functions to estimate here. So we're going to start with the first one. So for x0 and y0, well, you see we have the following vectors. So we have x0 that's here, y0 that is there. You see that the scalar product here is negative, and it's actually minus 1 over root 2. Okay, you will have to believe me for this calculation. So the scalar product is minus 1 over root 2. Combined with this minus sign here, we get plus 1 over root 2. And that's the contribution here for the first term. I'll do the second one, which is also 1 over root 2. Let's see. So you have x0 here and y1 here. So you see it's exactly the same thing. The third one, I have y0 here and x1. So it's again 1 over root 2, the contribution here. And now the magic part is the last one. because now I'm looking at x1, y1. Now the scalar product is positive. So it's actually 1 over root 2 in this case. With this minus sign, I get a contribution of minus 1 over root 2. So you see, I get 1 over root 2 everywhere, and the tricky part is that I get this sign right here in order to cancel this one. So if I sum everything, I get 4 times 1 over root 2. So this is just 2 root 2, which is about 2.8, and of course this is much bigger than 2, which was the local bound of the inequality, as we call it. So this shows that we have non-locality in quantum mechanics. So it means that the distribution that corresponds to this particular experiment, there would be no way for me to write it in this form here. So it does not admit a decomposition of this form. And the important thing is that this is no matter how complicated the program is. So no matter what this hidden variable is here, it might be even new physics, it doesn't matter. As long as I violate a Bell inequality, it means I cannot find a decomposition of this form. All right, so this is essentially the content of Bell's theorem. So there are quantum correlations which cannot be explained by a local model. So these correlations are non-local, which then means that they are stronger than any local ones. Right? So Bell's theorem says this: the predictions of quantum mechanics are incompatible with those of any theory that satisfies this notion of locality a la Bell. Right. So now an interesting question is the following. So in the previous experiment we saw that the score that we achieve is this. So let me go back to it. The score we achieve in quantum mechanics is this funny value here of 2 root 2. So 2.8, right? And something. I mean, of course, it's not rational. But you see, I mean, this is a sort of strange value. Where does it come from? What's the origin of this quantity? After all, if you look here, I mean, in principle, this quantity can be 1, 1, 1, this one minus 1. So one could reach 4 here, right? There is no reason why one would get 2 root 2. So it's a natural question to ask if the one we had, this strategy we had, is the best quantum strategy, or if there are actually better ones. One could use higher dimensional systems or more complicated states. Actually, it turns out that it's the best strategy, and this was shown by Zirelson a long time ago. So what Zirelson showed is that this CHSH expression here in quantum mechanics is upper bounded by some quantity here. Don't focus on the details, but I will just use this to make one point clear. And this quantity, once you calculate it correctly, you see that it cannot be bigger than 2 root 2. So indeed, this is the best one can do in quantum mechanics. And it's this bound actually, well, I chose to discuss it because it shows something interesting, I would say. It shows that the commutation relation between the observables, you see here there is the commutator between x0 and x1, y0 and y1, plays a fundamental role here. And you see that if you choose the measurements of Alice here, for instance, to commute, if this commutator is 0, then you are back to CHSH smaller or equal to 2. So you see that we had entanglement as a necessary ingredient for non-locality. Here we have another one, the fact that the measurements are incompatible. If the measurements on either side are compatible, there is no way you can violate Bell's inequality. So somehow, this is another interesting feature of quantum non-locality, the fact that when you observe Bell violation, you know two things about your experiment. You know that it contains an entangled state, and you also know that the measurement operators are incompatible. So somehow you highlight, I would say, two of the most distinctive features of quantum theory by such an observation. All right, so now we have seen that in quantum mechanics there is no way to go beyond 2 root 2 here. But as we saw before, by a simple algebraic argument, you see that in principle you could go to higher values. And Okay, so this makes us ask the question, what is the best possible score? I have answered this question already. So the best possible score is CHSH equal 4, because you would get 1, 1, 1, and minus 1. And now the question is, can we reach this bound in some way? Of course, we cannot do it in quantum mechanics, but perhaps in some more general theory, we could do that. And there is a simple way of reaching this bound by using an object which is now referred to as the PR box, the Popescu-Hörlich box. I will not discuss this in great detail, but I will need it a bit later for my discussion of loopholes. So this box is actually the perfect resource for playing this CHSH game. It does not exist in quantum mechanics, but still it has sort of nice properties, which we will see in a minute. So this box, okay, so first apologies, I have now switched from the physicist notation to the computer scientist notation. So now the input bits and output bits are denoted 0, 1. But it's exactly the same as before. Now, if in this notation you retranslate the rules of the CHSH game, you will obtain something like this. You would like the XOR of the outputs to be equal to the product of the inputs. So if you satisfy this relation perfectly, well, then you achieve the best score at CHSH. You get CHSH equal 4. Now, the nice thing about this object here is that it is no signaling, so it's compatible with relativity. And this is due to the fact that the outputs here are locally random. So there is a whole research on actually finding out why such a simple object does not exist in nature. So somehow why non-locality is limited in quantum mechanics. And I will not discuss this here, but there is a recent review by Sandu Popescu in Nature Physics on this topic, if you want to take a look. All right, so I will now switch to somehow the second part of the talk, and I will now discuss more experimental perspective on these topics. In experiments, you know, nothing really happens exactly like theorists wanted it. So there are always imperfections and technical details which make the experiment deviate from the theory. And in the context of Bell's theorem, this is actually quite important. And because at the end of the day, from Bell's theorem, we are trying to demonstrate that nature is inherently non-local, so that there are experiments that you cannot really explain by any sort of local model. So of course, this is a very, very strong statement. Now, when people perform experiments giving evidence of Bell inequality violation, well, then there are other people who are convinced that such phenomena are not possible, that try to, you know, find loopholes in these experiments. So they try to argue that the practical implementation does not quite match the theory, and that using these differences, it might be possible to reproduce the data, but conserving locality. So this is the idea behind all these loopholes that plague Bell tests. So as I mentioned earlier on, well, all experiments that have been done today are plagued by some loophole, but there is hope really to achieve a final loophole-free Bell test within 1 year or two, I would say. Okay, so what are those technical imperfections that open loopholes, and what are these loopholes? Well, essentially there are two, which I'm going to discuss today. The first one is called the locality loophole, and well, essentially this is due to the fact that in some experiments it might be hard to place space-like separation between your measurement stations. Therefore, it opens the possibility for signal to explain the data, and the way to solve this is to put them in space-like separation. Now, the second loophole, which is a bit more tricky, is a loophole that exploits the detection efficiency, or the observed detection efficiency, which might be quite low. For instance, if you think of photon experiments on long distances, well, the photon count rates will be relatively low. And this is a problem in this context because, as I will explain in a minute, a tricky model, so model that is quite malicious, but nevertheless physical, I would say, is able to simulate Bell inequality violation by exploiting low detection efficiency. We'll see in a minute how this works. So in order to address this, well, you will need sufficiently high detection efficiency, which you can get, for instance, in atomic systems, but I'll come to that in a minute. So let me start with the locality loophole. Right, so I'm coming back now to Bell's locality condition. So this is the condition we want to test, if you want. And now, well, as I discussed already quite a lot, I think, in order for that assumption to be tested in the way we want, well, we need to enforce that there is no communication between Alice and Bob. So that means that once Alice has chosen which, whoops, okay, not sure what's going on, but so once Alice has chosen which measurement to perform here, well, then the output here is produced in a way that doesn't depend only on X and on lambda. So that means that the information on Y and B cannot influence the way in which A is chosen. Okay, so mathematically this reads in the following way. I would like the probability for the outcome A to be chosen given those variables here, not to depend on Y and B, right? And similarly on Bob's side, I'm gonna ask a similar condition. Now, of course, this you can address in an experiment by having space-like separation. Then at least any model that is sort of consistent with relativity as we know it cannot then explain the violation that you see. There is actually another form of the locality loophole. Some people would argue it's a different loophole, but I would argue it's somehow related to the locality loophole because it has to do with the way in which the elements of your experiments are placed. And this has to do with the way in which you choose the measurement settings here. So note that when we wrote Bell's locality condition here, we made one assumption. Well, you may argue that it's quite a reasonable one, but it's still an assumption that the hidden variable here is chosen in a way that does not depend on the inputs X and Y. So mathematically it reads like this. So probability of choosing lambda given XY simply does not depend on XY. And you can understand why this is a problem, because if initially here, imagine now you're the provider programming the devices, if initially you know already what measurements Alice and Bob are going to choose, well, then it's relatively easy to provide measurement outcomes that are going to satisfy all the rules here of CHSH. So, of course, in this case, you can fake Bell inequality violation. So you need to ensure that your choice of measurement settings here, X and Y, is uncorrelated or independent from the source here. So one way of doing this would be to put your random number generators in a space-like separation from the source here. So this is a sort of additional requirement compared to the previous case of the locality loophole. Now, maybe let me make one comment here. So in any case, at some point, you will have to assume, if you want to test Bell's inequality in a satisfactory manner, that there are some elements which are independent from each other in the experiment. Because if the observers here are in some sense not free to choose what input settings they want to test, well then, it could be that just everything has been pre-programmed from the beginning of the universe, right? So you are not free to choose which measurement you want to do. And actually, the information about this choice is already contained in the source here because everything has been predetermined. And then, of course, you can explain whatever data you want with such a model. But I would argue that such a model is not very exciting, because then essentially, one of the main points of physics is that the observer has freedom to choose how he wants to test nature. Otherwise, it's a bit limited. So in some sense, it's interesting to see how far you can push these ideas here. So what is the minimal set of assumptions you need? But in any case, at some point, you will have to assume that certain sources are independent from each other. Otherwise, you will not be able to test these ideas. All right, so now let me say a few words about what has been done about this locality loophole in actual experiments. So, as you can imagine, the best system in this case are photons. And the reason is that photons, well, you can send very far apart. They do not couple very much to the environment. So this is perfect for having measurement stations which are far apart. Now, so shortly after the CHSH discovery, Clauser, who was the first author of that, with some, I guess he was a student of him, Friedman, performed, so they went to the lab, they knew about quantum optics, they went to the lab, created entangled pairs, and then tested Bell's inequality in a very simple setting. So they could not achieve space-like separation, so their experiment was plagued by the locality loophole, but nevertheless it showed already Bell inequality violation. Now, it was quite demanding at that time to achieve space-like separation, and this was done for the first time 10 years later, here in Paris by Alain Aspect, Dalibard, and Roger. And, well, that is probably the most famous Bell experiment today, because really, I mean, at that time, the locality loophole was really considered as the main issue. People believed that it was really possible to have a signal and so on, and therefore this experiment here had a strong impact, because it was showing that even with a space-like separation, you would still observe Bell inequality violation. Then, 16 years later, came two other experiments that somehow pushed the limits of the first Aspect experiment. So the first one was done in Geneva by Wolfgang Tittel, who is here. And this experiment was very nice because it showed Bell inequality violation on 10 kilometers. So it was a sort of demonstration that this is not only a lab thing, but really on huge distances you can see that. Another very important experiment was due to Gregor Weiss and colleagues in Vienna. And that experiment managed to enforce space-like separation in a stronger manner, even with the random number generators. And that had also quite a lot of impact. And more recently, there was an experiment done also by the Vienna group. One of these experiments performed in the Canary Islands between the three different islands there. And that one enforced, so that one managed to address this question about the source being space-like separated from the random number generators. So what I call the second aspect of the locality loophole, what some people will call the freedom of choice loophole. I have to say I'm not a big fan of this name here, but essentially you understand the idea what this means. So here I would say quite a lot has been done, and I guess now it's sort of relatively clear to most people. I would say that it's not a signal that is the explanation behind quantum non-locality. In this respect, there is also another interesting experiment which I can mention here. So it's an experiment that aimed at testing this idea of a signal explaining the non-locality that you observe with entangled particles. So the question that was asked is, really, is there some sort of spooky action at a distance? Is there a signal that goes from one place to the other? And this was an experiment done in Geneva. Here you have Geneva, the lake. And the experiment was done between two villages. One is called Satigny, the other one Jussy, which are separated by almost 20 kilometers here. And you see that the alignment between these villages is east-west. And now the idea of this experiment was to say, okay, now we want to test the idea that there is some sort of signal that goes in some preferred frame that explains the non-local correlations that we observe. Now, using the rotation of the Earth, right, you can scan by continuously monitoring the correlations here, you can scan lots of reference frames, right? Because, I mean, if you just do the experiment at one time, well, you can't say too much because you don't know where this reference frame, this preferred reference frame is pointing. But if you repeat the experiment, you scan many, many reference frames. And you see this was the data observed here. So you see essentially the visibility, which is essentially the same as the violation of Bell's inequality. And you see that the inequality is violated really for 24 hours here. So there is no drop in visibility. And this has interesting consequences because essentially it says that if there is a signal that really explains quantum non-locality, you see this signal has to go at least 100,000 times the speed of light. And this is true for a very, very broad class of reference frames. So it's essentially a very strong demonstration, I would say, that yeah, a signal is not the origin of quantum non-locality. All right, so let me go now to the second loophole, which is the detection loophole. So again, the idea is the following, is that if the observed detection efficiency, so the rate at which you get conclusive events, if this rate is too low, then a local model, well, it's quite a tricky one, but you will see there is nothing that is so crazy about it, then such a model can lead to Bell inequality violation. And this was found out by Philip Pearl quite a long time ago already. And although it was not taken very seriously at the beginning, I think people were mostly focusing on the locality loophole. Nowadays, I think this one is the sort of the most relevant loophole in Bell experiment. And just to give you an idea of why this is so problematic in experiments, for instance in photon experiments, well, the typical efficiency you need to reach in order to close this loophole, it's about 75%. So if you have experience with photons, well, you will see that indeed this is extremely challenging to achieve such a... And here I'm not talking about the detector efficiency. This is the overall efficiency somehow of one arm of the experiment. So this is indeed quite challenging. Okay, but let me make one step back and try to explain to you where it comes from, this idea of the detection loophole. And for that, I will do one example. I'll go back to CHSH, and I will now show you how you can program the devices, now exploiting this detection loophole, in order to fake Bell inequality violation. So here is the game. Remember that before, when we were trying to play the game here, we assigned outcomes. Remember, +1, +1, +1, +1. And then at the end, we concluded, well, we can satisfy 3 out of the 4 relation, but this one here is, okay, this one will not succeed. But now, so now again, you're the programmer. Now, in this setting, there is a new possibility that is offered to you. For each measurement, it's not only that you have to choose between outcomes +1 and -1, you can also choose not to answer. So you can say, well, I'm sorry, I lost the particle, I don't know. And this is exactly what we are going to do now. So on Alice's side, whenever we get measurement x1 here, we are just going to pretend that the particle was lost, right? Now, you see, of course, this is good for us, because now, in those cases in which we answered, so for instance, in this case here, or in that case here, well, we satisfy the relations, right? So there is no mistake that is introduced. Of course, in that case, we would have had a problem, but in that case, we just say, oh, I lost the particle. So essentially here, we have a strategy that exploits this possibility of not answering. Right? Now, of course, if you just use always this strategy, well, the observers are going to see that there is something wrong, because for measurement x0, Alice always gets some answer, but for measurement x1, she doesn't, right? So something is going wrong. But of course, you can now mix this strategy with others in order to make this inefficiency look symmetrical between the measurements. So here is another strategy. You would answer -1, -1, and +1 here. So you satisfy this relation and that relation. But here you do not answer. You pretend that you have lost the particle. Okay, so essentially you can symmetrize these strategies, use all possible strategies with the same idea. And you will see that indeed if you do that, well, whenever Alice gets an outcome, well, then you win always the CHSH game, right? So you have non-locality out of a local model, but really because you exploit this possibility of not answering. So overall, in such a model, we would have the following thing. So we would see that Alice's detector is going to click with probability 1/2, right? If you choose at random between these two measurements here, well, the probability that there is a click is 1/2. Note that on Bob's side, there is always a click, right? So here there is no loss of efficiency. And of course, if now one looks at the post-selected statistics, well, then you obtain CHSH equal 4. So you have very high non-locality out of this very simple model. All right, so the conclusion of this is that here we have an extremely simple model exploiting this detection loophole that reproduces exactly the PR box. So the moral of the story here is that post-selection, in this case, is a dangerous thing, right? Because in this tricky model here, you may use the fact, I mean, the devices may use the fact knowing that the observers will do post-selection in order to fake Bell inequality violation. So if you want to close the detection loophole in some experiments, it's really important that you do not throw data away, that you consider the whole statistics and that Bell's inequality is tested on the entire data. Otherwise, you run into this problem. So I can say something else. So far, in lots of experiments, people have still observe Bell inequality violation. So one way of getting rid of this problem, if you have an experiment with low detection efficiency, is to make the so-called fair sampling assumption, in which case you assume that the efficiency here of the detector does not depend on the question that is asked, right? Even for a fixed hidden variable. So that is the fair sampling assumption, which then allows you to prevent this detection loophole. But if you do not want to make this assumption, if you really want to go to a loophole-free Bell test, well, then you need to be careful. All right, so here I have a model in which Alice answers with probability 50%, Bob with probability 100%, and I get maximal non-locality, right? So now you can imagine that this model you can somehow symmetrize and so on. And then at the end of the day, well, you achieve a model in which each observer answers with some probability 2/3, and which again achieves high non-locality. So this means that if you do an experiment in quantum mechanics, and quantum mechanics is less non-local than this, well then you need an efficiency that is even larger, right? So it means that with efficiency lower than 2/3, there is no chance that you can ever violate the CHSH inequality because of this very, very simple model here. Now, there is another way of looking at this problem, which is somehow the other way around. So now I'm aware of this detection loophole problem. I imagine I do an experiment that is, okay, I imagine now I do the experiment we saw before, where I use the singlet here and the optimal measurements in those devices here. Now the only problem in this experiment is the limited efficiency eta. So now the question I ask myself is, what is the minimal efficiency I'm going to need here in order to close this detection loophole, right? So I know that I cannot throw data away. I'll need to keep everything. We're going to compute now how much efficiency I need to prevent from this previous loophole. All right, so the first thing you need to observe here is that in this experiment, I'm going to observe essentially 4 types of events. So we'll have fully conclusive, or let me call them conclusive events, in which case I get a click on both sides, right? In that case, I will observe the quantum statistics. I have also the opposite case in which I get no click on both sides. In that case, I will need to invent an outcome myself. And then I have intermediate cases where I get 1 click on one side and no click on the other side. And same thing. Okay, so what I will impose now, I will impose that the full statistics, so taking all these different events into account, that the full statistic violates CHSH. And this will give me this simple equation here, which I'm going to explain now. So remember the first cases is when I had clicks on both sides. Right? So this happens with some probability eta squared here. In those cases, I have the quantum statistics. Let me imagine I have a pure state here, the best measurements, in which case I get 2√2 for CHSH. Now I'm trying to compute the average CHSH value, if you want. So with probability eta squared, I get 2√2. This is the first contribution. Now the second types of events are those where I get no click. Those happen with probability 1 minus eta squared. And in those cases, well, I know that I have no click, but I still have to provide an outcome, right? Because I cannot throw data away. So in that case, I will just say, oh, when I get no click, the outcome is +1, right? This is my rule for inconclusive events. So if both Alice and Bob do that, if they always give the result +1, well, we know they will get CHSH equal to. This is the local strategy that we discussed before. So in those cases, well, this is the probability that such events happen, and in those cases, I get CHSH equal to. Now, there are the final cases in which I have 1 detection on one side and no detection on the other side. Now, in those cases, actually the CHSH value is going to be 0. The reason for that is that if you make a measurement on one side of a maximally entangled state, the output is random, right? So of course it's not correlated to anything that Bob does, right? And in that case, well, there are no correlations, so the CHSH value is 0. Now if you put these two things together here, so you impose that this average CHSH value is bigger than 2, well, you simply get that the efficiency has to be bigger than some threshold here, which is given by this expression, which is about 83%, right? So this is quite a high and challenging value for at least for photon experiments. So this is the minimal efficiency I need here to close the detection loophole for CHSH using the 2-qubit singlet state, okay? So of course this looks like, I mean here I'm considering one particular quantum strategy, which a priori looks like the best choice because this is the most non-local quantum strategy I can have. Now, a funny thing that happens here is that you may nevertheless ask what happens if you consider weakly entangled states. A priori, it doesn't look very useful, right? I mean, states which have some parameter here. The state is written here in the Schmidt form. And the funny thing that happens is that actually, it's not the best thing you could imagine to do to take the singlet state. If you take a less entangled state, well, you can tolerate a lower efficiency. It's an astonishing thing which was discovered by Eberhard a long time ago. But nevertheless, it happens. And people have actually exploited this. I'll come to this in a minute. So essentially what you see is that if you pick the angle here to be pi/4, the minimal efficiency is this 83% that we saw before. Now, in the limit of theta going to 0, well, the efficiency goes to 2/3, right? And you see that we recover this value of 2/3, which we know is the absolute minimum that one needs to have for CHSH. Otherwise, there is this simple model that we saw before. And really, the interesting thing is that the less entanglement you have here, the lower efficiency you can actually tolerate. So it's sort of a phenomenon that some people would call to have more non-locality with less entanglement. Why more non-locality? Because you can you can test your Bell inequality with a cheaper device, with a device that is not as good as the one you need for a more entangled state. So somehow it means that this state is more robust, its non-locality is more robust compared to a more entangled state. All right. I may also say, yes?
Doesn't that mean you can demonstrate Bell violation with a classical source?
With a
go to zero?
Yeah, no. So this is why okay, it's important that there is only this limit here. So of course you're right. Once you go to the product state, so for theta equals 0, well, of course then you have a local model. But so then you cannot have any Bell violation. But it's really when you tend towards the product state that you get this effect. Yes?
But I think there's also the point that if you tend to 0, your violation also tends to 0.
Sure, yes.
Somehow the amount of non-locality is how far above 2 you are, not just whether or not you're above.
Yeah, I agree. You could see the 2 points. I agree. The 2 perspectives are good, I think. So on the one hand, you can say that state here is going to lead to higher Bell violations. So it's more non-local than such a state here. But on the other hand, you know, the amount of Bell violation is just a number, right? So if I multiply everything by 2, do I get more non-locality? Well, no, I guess. So somehow it's useful to think of more operational measures if you want to quantify non-locality. And well, this might not be the best one, but I think it's a valid one. You know, what type of detectors, what type of efficiency do you need to reveal the non-locality? And if you can tolerate lower efficiencies, you would argue that the state is more non-local in some sense. All right, so far here we have discussed threshold efficiencies for CHSH, but of course you may imagine more complicated Bell experiments, right? Because of course the hope is that you may achieve lower values than those ones. And people have considered this, so a Bell experiment with 1,000 settings and so on. A problem here is that we do know only very few Bell inequalities, so it's a hard problem in general to tackle. But nevertheless, few things are known. So if we look at more sophisticated Bell tests, there are a certain number of parameters we can play with. So one parameter is the local Hilbert space dimension of the state. So let me take states of dimension d by d here. I take m measurement settings and k outcomes, right? Of course, one could also go to the case of more parties, looking at GHZ states and stuff like this, but I'll not discuss this here. So here there are 2 results which are probably more interesting from a theoretical perspective, but nevertheless. So in quite a few years ago, Serge Massard showed that there indeed exist Bell tests for which the efficiency goes to 0. So the efficiency that you can tolerate goes to 0, but for that you need the dimension of the systems essentially to go to infinity. So with this you can reach, and okay, I didn't write it, but you will need Bell tests with lots and lots of measurements and lots of outcomes. So I didn't write it here, but if you use Massard's work here, and you ask how many dimensions, or how complicated is a Bell test that I need to achieve, say, 10% efficiency or something like this, or 1% efficiency, well, you get Hilbert space dimensions of the order of 1,000 or something like this, and probably 10,000 measurements. So you see it's not feasible in practice. And then there is another thing that is known here. So in this paper here, it was shown that, so you see here, I have made the situation slightly more general compared to before, because I have discussed a different efficiency for Alice than for Bob. And this might be relevant, for instance, if you have a hybrid type of entanglement. So if you have entanglement between an atom and a photon, because you would have a different efficiency for atomic measurements than for photonic ones. So in that case, Well, the efficiency can also decrease very quickly, so it can go to 0 here. And another thing that is known is that so this is slightly more realistic Bell test. So it would be a Bell test in which you use 4-dimensional entangled state, for instance, hyper-entangled systems. Then you would need just 4 measurements, which are binary, and you could tolerate an efficiency of 60%. So you see it's already a bit better than CHSH. It's a bit more complicated as well, but at least that one would be feasible. And I'm not saying that this is great, but I'm saying that this is the best we have so far. So for practical Bell tests, we do not know of anything better. Now, of course, this has not prevented people to actually close the detection loophole in experiments. At first not with photons, of course, but using atomic systems. And the reason here is that for atomic systems, you have unit efficiency, so you do not have these problems. So you have no detection loophole. And the first experiment done this was done at NIST here, and here you have a picture of the 2 ions used in the experiment. So you see they sit in the same trap, so although you close the detection loophole here, there is no hope to close the locality loophole, because each atom can just feel the other, so because there is absolutely no space-like separation. Now, big progress was achieved in this, in particular in the Munich group of Harald Weinfurter, who managed to do a slightly more complicated version of this experiment, but achieving a separation of 20 meters. So there the 2 ions sit in different traps, and still they violate Bell's inequality. Other systems that were investigated are superconducting qubits, not describe this. What I will describe a bit more is that recently with photons, people have managed to also close the detection loophole. So to achieve an efficiency of about 75%, which is indeed quite tremendous achievement. And this has been done in the group of Paul Kwiat in Illinois, and also in Vienna in the group of Anton Zeilinger at about the same time. Sorry? Exactly, this was using Eberhard's idea. I'll come back to this in a minute. Now, this is quite nice because now photons are the first system in which the 2 loopholes have been closed individually. So it's quite nice. It's still not the ultimate thing we want, because we would like to have the 2 loopholes closed in the same experiment, but there is quite some progress in this direction. I will skip this. Okay, so in the last few minutes, I will discuss progress that has been done recently towards achieving a loophole-free Bell test. So here is the setup of Paul Kwiat, actually, so the Illinois experiment that closes the detection loophole with photons. So in order to do that, one needs superconducting detectors. And the overall efficiency just about reaches this limit of 75%. So in this experiment, the Bell violation is really, really small, but nevertheless, the test is conclusive. And so coming back to Gilles' question, so here you see, so in this experiment, it was actually crucial to use a partially entangled state with just the right amount of entanglement in it. Remember that for a singlet, one needed 83%, so this would not be good enough. But by weakening the entanglement, it becomes good enough. So here is a graph which shows Bell violation. So this is the Bell limit here. The scale is different, but it's not a big deal. And here you see the entanglement. So for high entanglement, you see no violation. Now you lower the entanglement, and here there is a very, very small violation. And it was the same thing it was very similar to what was done in Vienna. Okay, so now what would one need to do a loophole-free Bell test with this experiment? Well, actually, it's not that trivial, because at this moment, or during that experiment, the 2 detectors were actually sitting in the same, so these are detectors that need to be cooled to very low temperatures, and they were sitting in the same cryostat. So now, if you want to do a loophole-free Bell test, well, you would first have to separate these, so get another cryostat, and put them at distances which I think are of about a few hundred meters. So given that the losses are already just about what one can tolerate, just adding these few complications is not that trivial to achieve a loophole-free Bell test starting from this setup. But I think Paul is working on it, and in Vienna as well. So we will see if that becomes possible in the near future. Now, another experiment that is promising is the one that exploits atom-photon entanglement. So this is essentially the setup of Harald Weinfurter in Munich. So the idea is like this. You have two atoms here sitting in distant traps. And now the atom here is excited in such a way that when it de-excites, it emits a photon to which it is entangled. So you have atom-photon entanglement here, atom-photon entanglement here. And then you just do entanglement swapping by combining the two photons at some intermediary station here. And then you obtain atom-atom entanglement, which we call event-ready, and then you can do measurements and violates Bell inequality. So in the Munich setup, they achieved this recently with a separation of 20 meters, achieving a fairly high Bell violation. Let me mention also that there has been progress in this direction using another system, which are NV centers. And I think Ronald Hansen will tell us about some progress in this direction. Another system that was seen as a very good candidate for loophole-free Bell test were optical continuous variable systems. The idea being that there you have very high efficiency measurements because you do homodyne measurements. I will not go into details here, but the conclusion is that there has been some progress on both on theory and experimental side, but it's still very challenging. So I think today it doesn't look like the best candidate for the first loophole-free Bell test. And another system that appears to be interesting is to look at spin-photon interactions, so which you could have in quantum dots or NV centers or atoms. And here the idea is essentially the same, well, it's similar to this one here, where somehow you combine, I mean, one would argue that you combine the best of both worlds, right? You use atoms because they can be measured with high efficiency, and photons because you can send them far apart. But in this other setup here, you would somehow do the opposite. So you would start from photonic entanglement. Now, you use this spin interaction, for instance, in cavities, which would allow you to map the photonic entanglement to spins. And this you can do, in principle, in a heralded way. And in that sense, you will manage to prepare distant entanglement between two spins, which you can then measure efficiently. And I think that would also be quite a promising setup, in particular for certain applications. All right, so I will now go to the very last part. So I've shown you here that there is some progress towards achieving a loophole-free Bell experiment. Hopefully, it will be within a year or two. And so beyond the fundamental interest of these studies, another interesting thing is that a loophole-free Bell test would also actually be the starting point for a whole new class of protocols that could be implemented, for instance, for cryptography and randomness generations. And those are protocols which people now call device independent. And the idea in these protocols is that the security is based by checking some Bell inequality. So essentially, this allows you to do something that's interesting, is that you can guarantee the security of some protocol without relying on a detailed knowledge of how your devices work. So you do not need to know exactly what alignment you have, and perhaps there might even be some side channels and so on. So in principle, device-independent protocols should be immune against those kind of attacks. So here is again the idea. I won't go into details, but the idea is that by checking Bell inequality violation, essentially what you are going to assess is that the outputs here of Alice and Bob are locally random and uncorrelated from some adversary. Now, of course, because this relies on Bell inequality violation, loopholes are important here. And if you think in terms of testing Bell's theorem from a fundamental perspective, one may argue that nature may not use incredibly tricky strategies to fool us. But if you think of an adversary, well, this becomes much more natural. So here you will have to be careful for loopholes. Let me just say 2 words. So from the point of view of the locality loophole, I think one would argue that it's not so crucial in the context of device-independent protocols. And the idea is that in any case, in such protocols, you will have to be careful that there is no leakage of information to the adversary. So in that sense, you have to prevent that there is somehow no signal going out of your lab. So the locality loophole will sort of be dealt with by these kind of considerations. Now, the detection loophole is much more important here. And in order to emphasize this, it was recently reported in actual experiments how you can actually create fake Bell inequality violation by exploiting the detection loophole. So of course, there was this very simple strategy that I explained, which, okay, is a sort of toy strategy. But in actual experiments, exploiting the physics of wave plates and detectors, you can actually mimic very easily these kind of things. So really, it would be important to close this detection loophole. Yeah?
When you fake these Bell inequalities, in fact, because you're completely classical, so what do you care about wave plates or any of the objects? You do the whole thing completely classical.
Yes.
What's the challenge?
Well, that's true, but I think what these experiments show is that because the setup, it doesn't look like my basic strategy here. It looks like an actual physical setup.
You don't use.
Well, you do use, and I think the moral of the story is that if you're not careful, there might be side channels that are exploited in a way that you may not notice a priori, but that somehow, when you first look at the experiment, you wouldn't think that there is something going wrong there. And somehow, well, I think it shows in a quite convincing way that it's quite easy to be tricked in such a situation. But okay, on the other hand, I agree with your point. From a more theoretical perspective, this model is good enough. All right, so for the implementation of these protocols, few things have been done already. So for device-independent randomness certification, there was an experiment based on this atomic configuration that managed to extract 40 bits in 1 month, because the count rates in such experiments are very low, but these are really just proof of principles. And now with the photonic experiment, in principle, one could also certify randomness in this device-independent way. Now for QKD, this is way more challenging, so here nothing has been done yet. All right, so come to the end of the talk. I've talked quite a lot about Bell's theorem, loopholes and experiments and so on. For further references, so here is a review that we wrote with few people that just appeared in Reviews of Modern Physics. If you are more focused towards loopholes, you could also check this review of Jan Åke Larsen, which is going to appear in some special issue of JPhysE. Thank you very much.
I heard something in the last few months about an experiment with detectors triggered by light coming from cosmic sources. Can you explain it a little bit? Is it another loophole or?
Okay, so
what's the principle?
okay, the idea there was so remember that there is this so-called freedom of choice loophole, where the choice of settings might be correlated to the source already. So people have suggested to use light that come from different sides of the universe, and that they argued could not have been correlated in order to generate the measurement settings. So that would be to enforce this freedom, I mean, to close this freedom of choice loophole. But then, because of other theories like inflation, for instance, it may actually not be the case that these two distant locations are never interacted, that they are completely independent. So in some sense, it's a cute experiment, or it's a cute proposal, but how much it adds to the demonstration of quantum non-locality, I'm not completely sure.
Nikolai, you mentioned work towards closing the locality loophole at the same time as the detection loophole. And you mentioned that it's the detectors that have to be space-like separated. But one could certainly also argue it should be the measurement devices themselves. What's your opinion on that? And do you know what the approach in Paul's and Anton's group is? And maybe that question is actually rather for Paul than for you.
Well, I guess the approach, okay, so first I agree with your point. It's a whole quite interesting discussion about which place has to be in a space-like separation. I think to be on the safe side, both experiments will just put everything in space-like separation. So really just to have the most natural setup where you really have one measurement station here and another one there. And I think it would probably also not be convenient then to bring back the photons to a detector that would be placed in the center or something like this. Perhaps you would have more losses, but Paul can probably tell you more about this than I can.